The case is described on this website. So it's still the same case with the flat plate, inlet. We are given total pressure and total temperature. Outlet, we are given the outlet pressure. We have an inlet, a small section that is treated like a symmetry, and then there is a adiabatic nozzle small. This is our plate, where we have the development of the water boundary layer. And instead of the top, this is a far field, so we treat it like a symmetry. In this case, so what we are asked here is to calculate the Walsh infiltration coefficient. So that's CF, so the same parameter that we have calculated also during the previous exercises for different Reynolds theta. So we need to calculate once again the theta, so the displacement thickness. We need to calculate the Reynolds number based on that displacement thickness. And so we can relate the skin friction coefficient to it. And then also once again we need to calculate or show the load of the wall at Reynolds theta equal to 10,000. So we have to plot U plus versus Y plus. There are the equation. And we can compare all these results with theoretical values or experiments. So they are given still in the websites. Over here, these are the charts. And then here you also have links where you can find the data points for this. For both the Reynolds theta versus CF and then the load of the wall. Let's see what else. Then we should do this for two different grid resolutions. So while so far we have only used one grid, for this exercise you need to do it like twice. Basically it's the same procedure but with a different grid. And in Moodle you can find these two depths. Right? So the first one, the 273 times 193, is the same one than last week's. Then the second one is a finer grid. So it's going to take a little bit more time to run, and well, you can compare basically the results that you obtain with these two grids. Okay. And also using this two different grid resolution, and also you have to show the distribution of K, so the two best kinetic energy, epsilon, dissipation rate, omega, the specific dissipation rate, and nu-T, so the eddy viscosity. And you can find all of these variables also in Fluent. I'll show you how to find them and plot them. So we can start. First, I created here a folder where I'm putting the two depths files. I'm going to show you the solution only for one grid, but it's basically the same procedure also for the other one. Well, also since it's the same case that we have simulated so far, if you have previous case, you can even load like the previous case you set up already, like last week's. So you don't have to say to start from scratch, but you can just make the needed modifications to that case. So we can start Fluent.
I have the 2025.
Here I Control C and copy paste the working directory. This is a three-dimensional case with double precision. So I can start then Fluent. basically also with the Excel that we are going to create later, like for the post process, it's the same Excel that we have used like during last weeks. So if you have that Excel, you can just copy paste the new results that you get with the new models. So you can. It's going to be quite straightforward if we have already done for the previous models. I think this I haven't shown it so far, but you haven't also asked how to read or save a case and data file. So in front you know that you have a case that basically it's the file where you are setting all the settings of your simulation, and the data files that contains the solution data. Once we create the case, typically we can write. We have this file write. You can write case and data, and if you have that ready, then if you have already made case and data, you can read them. Yeah, from file read case and data. So I'm starting from scratch. So I will read my dev file. So I need to go from import CFX definition file, because they were created with CFX. And well, I can select one of the two and select this one. Is going to be quicker to run. And I can display the mesh, make sure that it looks fine. Before starting, in this exercise we need to use the standard K epsilon and K omega model. If you want to know more, let's say, of course you can just select the option there and run the case, but I think this is more for the project rather than these exercises. But if you want to know more about the theoretical, say, background, how these models are built, what's influent, so which equations are solved, you can go in help here in the question mark, and there is this user's guide contents. So apart from the lecture slides that Tim was showing at lecture, here you can get another look, let's say, at the models that are implemented in Fluent. So here, for example, in the search Fluent user guide, here you can search. Here I have these turbulence models. Let's see what comes out. When I search for that, by default, there is this filter only for the user's guide. So I'm going to cancel that, so that I also can get the results for the theory guide, not only for the user's guide. For example, here you can see that there is this chapter 4, which this is turbulence. So here you have basically all the models that can be used in Fluent. Last week we used Spalar-Tamaras. This week we are going to use the standard K epsilon model and the standard K omega model. So if I click on one of these, here I can find all the theory. Let's select the standard K epsilon. Then there are other modifications that you'll see probably next week, or you have already seen something maybe this week, I don't know. For sure, next week I think you'll see the K omega SST model. That is, let's say, the most popular of the turbulence model that is used nowadays. And here you can see, for example, for the standard K epsilon model, the equations that are solved. So for the turbulence, kinetic energy, and the dissipation rate. So these are the equations that you have already seen in the lecture. And you can also find some small additions to how the models are, what are the models constant, and how, for example, the eddy viscosity is calculated based on K and epsilon. And well, basically there is plenty of stuff if you are interested in. Okay, so for this exercise, you can even run without knowing exactly which equations are solved. as long as you get a good solution. So that's what we are going to do for this exercise. So first of all, I'll set the material. So in materials, I go to fluid air. Instead of constant, I'll use a ideal gas formulation. So it's a function of pressure and temperature. And then I change create. So now, also in the console, I get the message that the energy equation is enabled. Now we can go in models. And in models, we need to change the viscous model, which is the turbulence model. So I'll show you how to simulate both cases with K epsilon and K omega. With K omega, that is by default selected here. By default, it is selected the SST version of the omega model. But in the exercise, we're asked to use the standard version, so we just change to standard. And we make sure that production limiter is enabled. By default it is, and we hit OK. Then next thing I do is always I change in cell zone conditions. I double click on that and I change the operating conditions. Operating pressure, instead of the atmospheric pressure, I set it to 0. So I can set my boundary conditions now based on the values that are shown on the whiteboard. So here on the right top you have this button where you can actually group the zones, like the boundary condition by zone type. So you can see that, okay, here I have my inlet. By default, this is a velocity inlet. We need to change that to a pressure inlet. Yes?
Sorry, could you repeat the last step after the operating pressure?
So I selected the operating condition to 0, the operating pressure.
Okay.
Then I was going just to boundary conditions, and I was grouping the boundary condition by zone type. It's just to looks better, so you know what kind of boundary condition are in your domain, and they are grouped by their type. So in inlet, I need to change the type of that. So from velocity inlet, we need to use the pressure inlet boundary condition. So we change that. And we just need to set here the gauge total pressure. So that's going to be 1.02828 bar. So E5 to the power of 5. And then I copied this one also in the initial gauge pressure for the initialization. And apply. Now that we are running a two-equation turbulence model, you see that I need to set also the turbulence boundary conditions, and there are two boundary conditions for the turbulence, which is the turbulence intensity and the turbulence viscosity ratio by default, or there are also other alternatives if you have different boundary conditions for that. Typically, I don't touch this unless I know that I want to change these values. So this, I leave them by default, like the turbulence intensity 5%, which is a small value, say, and turbulence viscosity ratio is the ratio between the eddy viscosity and the molecular viscosity. So I can leave that to 10, like by default. And so I apply, and then in thermal, this is already correct, 300 Kelvin, so we don't change that. The next boundary condition we need to change is the outlet. we have already pressure outlet, but we need to still edit the magnitude of the gauge pressure. So that's 1 bar, so 1E5. And also in this case there are some other boundary condition specification, but these are for backflow. Again, this is not the case, we don't have backflow for this case, so we can just skip all the other. Then we have far field. This is on top, which is a symmetry, like it's correct. Then we have symmetries on the lateral surfaces. Symmetry at the inlet, so the small surface before the plate. And then the plate, that this is, has to be an adiabatic no-slip wall. And by default it is, so that we make sure that in the shear condition there is no slip enabled, and the heat flux is equal to 0, so that there is no heat transfer between the plate and the fluid. Alright, then we can go in methods. So methods, you can set the schemes that you want to use for solving your equations. By default, for this case, they are all second order. So these are quite accurate enough, so we can leave them by default. And I typically run this case with coupled formulation and a global time step. So there is a pseudo-transient formulation of the transport equation. So it's more stable typically than segregated solvers. For different versions, this can be a little bit different. I don't know, for example, in your fluent version, if this is global time step, you can define, or there is like the option pseudo-transient, that's basically the same thing. Then in controls, we also don't change these things, they are all the same. Next, we can add, for example, in report definitions, typically to check the convergence of the solution makes a physical sense. I check with a new report definition for flux report, mass flow rate. I can call this mass imbalance. So this is going to be the calculation of the mass flow rate at the boundaries. Here you can set inlet and outlet. So that the mass that is entering the domain is also exiting it. I'm checking that. And here you can create either a report file and a report plot. I don't need the report file, I just want to check the report plot, so how that looks. And okay. This is not, let's say, fundamental things to get the solution, but just to check that the solution makes sense. And it's converged. Then in monitors, you can double click. There is a residual. So I'm going to change the residuals that Fluent is checking every iteration if the convergence is met by the by residuals. So we are going to set this to 10 to the power of 5, all of them, which is low enough, let's say, for this case to ensure that we have a convergent solution. Okay. And so now we have set up the case. We can initialize it, we go initialization. We can use the hybrid. Typically use the hybrid is a good way to initialize the problem when you have pressure at both inlet and outlets. If you have different boundary conditions, for example, at the inlet you have mass flow rate or velocity inlet, that doesn't really perform very well. So maybe you want to go with the standard initialization, but in this case we can use this one. And then you can run the calculation. So with the pseudo transient formulation, here we need to set the timescale factor. If you use a time step automatic method, or if we know exactly like which time step we want to use, we can even use this specified, but we can go with the automatic for this case. We don't need to change that. And the timescale factor is just a factor so that if we want to reduce, for example, our time step, then we can just reduce this value. So we are reducing it by this factor, or increase it if you see that the solution can converge faster. Then we can select the number of iteration, I select thousands. Still the problem will converge before that. And so we can run with the standard k omega. This is for the standard k omega. So there we have two new tabs, one for the residuals and one for the imbalance plot. So you can see that the imbalance plot here it's already close to 0, so it goes to 0 quite quickly. And the residuals also go down quite rapidly. There I got the convergence for this model in 111. Yeah.
Yes, of course. It's different from man to man. There's something wrong. You can ask me. What's his name? Timo. Kiss. Kiss it. Kizzy. What's the name? Petrusili. Yes.
Yeah.
I think yes, there's something wrong.
Yes.
Different.
Yeah, seems like it's check the model to use standard formula.
No, it should be 1 point, right?
No, that's when you set like from E5 that
Yeah.
changing like automatically. Oh, yeah, here it's missing the outlet static pressure, so this is 1 bar.
Oh, okay.
Now it will probably work.
Thank you. But we don't have the third graph.
That's it doesn't really matter
Okay.
as long as the residuals are low. I would maybe let's see. Okay, it's already converging. Fine. For the graph, you can create that in report definitions, where you can create some different plots if you want to check like how the solution is
Okay.
evolving.
Thank you.
Seems better.
Thank you.
Now to check the solution is correct. Since the case is the same,
This is similar to problem 6.
we're always given that the Mach number in the free stream region is equal to 0.2. So we can check that. And we can, for example, in graphics, we can create a contour of, we change pressure, we select velocity. And instead of velocity magnitude, we select Mach number. Then there is this button over here with the tick that you can select all shown. So basically you can select all surfaces where you want to plot the contours. Save display, so you get this chart. Here in view, I also disable lighting, so that looks better. And the Mach number here should be 0.2. So if that's correct, then your solution is, at least it's what you should expect in the free stream region. Then we can check what is happening now in the boundary layer. Okay, so this is for the standard K omega. And as I was mentioning, now we can save the case and data file. So I can go to File, Write, Case and Data. And this is K omega. I just call it like that. So we save now the case file that can be read again, that file that contains the solution data. We were asked to also to use the standard K-epsilon model. So the case is exactly the same. The only thing that we need to change is in models, in viscous. We need to select the K-epsilon model. By default, you get that this is using the standard version of the K-epsilon model. Then we have near wall treatment. So, have you seen wall functions during the lecture or no? Yes. So the short recap. So this is our plate. We have our grid. Now I'll zoom into it so that we have several cells. So this is the one closest to the wall, and we want to capture, let's say, the flow distribution in this region. Let's assume this is the velocity. And of course, if your first cell is small enough, you are able to capture this distribution, this velocity distribution close to the wall. But what happens if this cell is not that thin? It's not that small. So you can't actually capture the velocity distribution, so the law of the wall. So in that case, for the chemical model, you saw that there is no near wall treatment. That's because it's automatic. So if your cell is too large, it's applying the wall functions automatically. So it's not asking, let's say, for you to set it up. For the K-epsilon, instead, you can choose either to choose the standard wall functions. That means it doesn't matter how thin the first cells are. We are still solving the boundary layer using wall functions. And then we have scalable wall functions instead, that by name has how the name says it's scalable, so it depends on your grid. So if your grid is fine enough, you are trying to resolve and not model the boundary layer. Then there are other also wall treatment. I'm not exactly sure how these are. Maybe these are a little bit more for heat transfer problem or something like that. You can find, by the way, every explanation for these terms also in the Fluent theory guide if you are interested in each of these near wall treatment. For this case, we are going for we'll use the scalable wall functions. And you should also enable this production limiter. If you don't do that, you will get some convergence issues for this case. So with this option, that will work for the standard axiom. And okay. Then, since we already have simulated one case, so we have already the solution for the k omega, we don't need to reinitialize the solution, but we can just calculate, so we run the calculation once again. If you have a previous solution, for example, but it's not loaded in Fluent, then you can just file, read data, so you can load a previous solution that will initialize your problem, so you, let's say, get convergence in a shorter time. If the solution, the initial solution is much more similar to the final solution, then it's easier to get convergence. So I can calculate. You can see by changing the turbulence model, the solution is changing, so but not that much, so I got the convergence in a quick time.
I think we change the model. That's right. Just change the k epsilon.
I can check again in contours that the solution makes sense. So that I get Mach 0.2.
And then initialization, right? Initialization, or calculation.
And then I can also save, so I can file, write data. Yes.
For the epsilon residual, is it that we leave it in the 1 to the 10 to the power of minus 4, or we change it also to the power of minus 5? Because when we change the model, I think the omega is changed to epsilon residual.
Yes, that's correct. So the residuals for turbulence are typically, you can leave them a little bit higher. That doesn't really matter. Yeah, of course you can change that in the
Monitors.
yeah, monitor residual. There you can. Now, since you are using a different transport equation, so while before we were solving a transport equation for the specific dissipation rate omega, now we are solving for epsilon. So that's another equation. So when you change the model, you're also changing the criteria for convergence. So you can set this also to 10 to the power of minus 5.
Minus 5, right?
And also in methods, actually there is, you can see that when I change it, when I switched from k omega to k epsilon, the turbulence kinetic energy and turbulent dissipation rate schemes, now they are first order. You can change that to second order again if you want like a more accurate solution, but for this case I think it's also first order is enough. So I can finish to run the case, reach the power of minus 5 also here. So once you get the convergence also for the k epsilon, you can write case and data also for the k epsilon. but that they are now distinct files for that. So if you want to switch between the solutions, you can do it at any time. And you should do the same, basically the same procedure for the second grid also. This is like as a homework, so you can then, unfortunately, when you are reading the new grid, you can't keep, let's say, the same solution, but you can keep the same settings. So if you can, from this state, we can just import CFX definition file. Or, no, actually, no, I'm sorry, I said something wrong. You can do that if you have a mesh file. So when you have a mesh file, you can just read the mesh, and you can just escape the data and replace the mesh. That means that your settings are kept in your Fluent. But in our case, we don't have a mesh file, we have a definition file. So when you are importing CFX definition file, if you select this one, then the case, I think it will be erased. So you can try that. Let's check, for example, materials. Yeah, you can see that, for example, the hair is not an ideal cast anymore, so then also the boundary condition, everything is reset. So you should set it again for this new def file.
What do you mean?
You can do this like yep.
I'm sorry, could you repeat the last step after
Yes.
after
so
file CF for importing the second file?
Yeah, so you are asked here to simulate this case with two different grid resolutions. So you have also a second def file, this 445 times 385. And this is a def file, so it's not a simple mesh file. So when you import it from file, import CFX definition file, your Fluent settings are lost. So you need to reset all the case from scratch.
Okay.
But this is only because we have this def file. If instead of a def file we have like a standard mesh file, then instead if you read mesh, you read the mesh file, your settings are still there. So it's easier to switch, to change the mesh and getting the results, just hitting read mesh and then calculate. But that's not possible for this case. Okay, so now I'll go back to, so I read case and data, I read my A epsilon, case and data. Okay, so by doing this now I'm loading again the settings and the solution data files. And we can proceed with the post-processing. So the post-processing, as I was mentioning, is exactly the same, the exactly the same procedure that we have done last weeks for the last two exercises. So I can show it again. So we need to first create some lines where we are going to plot the solution. So we can go in domain, surface, create line rake, and in here we can create different lines. Yeah.
Which case are you showing? K omega or K epsilon?
Not K epsilon. I loaded the K epsilon model. But the procedure is exactly the same for both cases. And once you create these lines, you can just read the data also for the K omega model, and you don't need to, let's say, recreate the lines or contours. So the first line we can create is the center line, so the one that goes in the middle, through the middle of the plate. I forgot to write the coordinates here.
I'm sorry. The first one.
So the center line is minus 0.50, and this is the first hand point, and the second hand point is, here we can set a high value of x minus 0.5 and 0. Instead, for the
This is 2.
other lines perpendicular to the plates,
Okay,
you can set this to x minus 0.5, 0, and here x minus 0.5, 0.1 to cover the boundary layer